This lesson sometimes seems to give students some trouble, and I promise it's not so bad. Let's go over them. Some examples that you might see on your assessments. Okay, what is the best linear approximation for f of x equals the cotangent of x near x equals 3 pi over 4? When you see the words linear approximation, you should be thinking equation for the tangent line. And an equation for a line is point-slope formula. I mean, you could use slope-intercept, but many times you're not given the y-intercept, so why bother with that one? You just need a point and slope for this one. And you're actually given enough information here to find both of those things. So first of all, the point, the x-coordinate is given to you, and that's usually always the case. The y-coordinate is going to be when you plug in to your function, and then the slope is the derivative at that point. So we have the function, we would just need to find the derivative and then plug in 3 pi over 4. So let's do that. Let's do the y-coordinate first. So the cotangent of 3 pi over 4, you could do that, or you can think of it as 1 over the tangent of 3 pi over 4. Either way, we're here in the second quadrant of the unit circle, and the pi over 4 angles are the square root of 2's over 2's. It's negative for the x-coordinate, positive for the y-coordinate. This ends up being, tangent is negative 1 here. Cotangent is also negative 1 there. So this y-coordinate is negative 1. Check. We're done with that one. The derivative of cotangent is cosecant squared. So now we need to plug in our 3 pi over 4. Cosecant squared is 1 over sine squared. And again, we're here in that second quadrant. The y-coordinate is the sine. So we're going to have 1 over the square root of 2 over 2. Well, after we plug in the 3 pi over 4, of course. I'm ahead of myself. Sorry about that. Okay, so if you square this, you end up with 2 over 4, which is 1 over 1/2. Multiply by the reciprocal there, you end up with the derivative equals 2 at that point. So we have this as negative 1, and we have this as positive 2. Check, and we were given this already. So plug it in. Y minus negative 1 equals 2 times x minus 3 pi over 4. And we can simplify this a little bit. I distributed. You don't even really need to do all this. Like, depends on the situation. If you're asked to simplify, then that's where I would stop personally. If there's no indication of where, like if you need to write it in a certain form, I would stop at the step above it. Maybe make that +1, but you don't need to distribute. However, if it's a multiple choice question, then you probably have to make it look a certain way. And in this case, I believe it was solved for y. So I'm going to move this positive 1 and make it negative 1 on the right side. And then get rid of that fraction by multiplying everything by 2. So that this will cancel. This will become a 2, this will become a 4, and this will be a 2y. Multiply everything by 2. Then you get this. And that should be one of your choices. Let's do another one. If f of negative 1 equals 4, so there's a point at negative 1, 4, we're given a point, and we've got a derivative equals that crazy looking fraction. What is the best approximation for f of negative 1.02 using linear approximation? Again, those words, linear approximation, means to find the equation of the tangent line. They gave us the point, which was really nice of them. X equals negative 1, this equals 4, and they actually gave us the derivative right here. That's so nice. Let's plug in that negative 1 and find the slope, 1x equals negative 1. It's kind of icky. You end up with 4 times negative 1 cubed plus 3 times negative 1 squared, 2 times negative 1 plus 1 down here, and you have to square all that. Simplify it. We end up with -1 there as well. Okay, so now we know this is 4, we know this is -1, and we know this is -1. Perfect. This gives us an equation for the tangent line. Distribute that, and that's how I got the -x minus 1 there. I'm going to add the 4, have it in slope-intercept form, because that's how people like to see it usually. And the reason I solved, actually, because now they're asking, what is the best approximation for this value? So think about what this is. This is the equation for the tangent line when x equals -1. So like if our curve looks like this, here's -1 right here on the x-axis. Here's our tangent line. Let me put that a little bit closer to the point. So this is at -1. The point at -1.02 would be like right there, like super close to it. Look at how close it is to the tangent line. So we don't have the actual function f of x in this case, but we do have a tangent line at a point super duper close to this point. So the tangent line and the function itself are like so close to each other, it's actually touching at -1, but 2/100 units away, it's going to be really, really, really close. So this tangent line is a good way to approximate the value of this function at that point. So if you have the equation for the tangent line, you just plug in that number into the tangent line equation. And that's how you get a close estimate of what f of -1.02 would equal. So because the tangent line is touching the graph of f of x at x equals -1, we can use it to estimate the location of the point on the f of x graph, just because it's going to be so close. The tangent line and the graph are on top of each other when x equals -1. When it's -1.02, it's literally hundredths of units away, so it's still going to be really close. Hopefully that clears that up. Next one. The radius of a sphere is claimed to be 8 inches, correct. The radius of a sphere is claimed to be 8 inches, correct to within 1/100th of an inch. Use linear approximation to estimate the resulting error in the volume of the sphere. Okay, this one just kind of has a strategy to follow. We're estimating the error in the volume of a sphere. That's the formula for the volume. This is the derivative of the volume with respect to the radius. So if you've seen other videos that I've done, I've talked about implicit differentiation. We just took the derivative of the volume with respect to the radius. We took the derivative of the radius with respect to the radius, so there's like an invisible 1 right there. And these are called differentials. You can kind of treat it like a fraction, multiply. And that differential is the error. So what you do is just plug in what they give you here. They give you the 8 for the size of the radius, and they tell you that it's correct to within 0.100th of an inch. I'm sorry, 1/100th of an inch. Let me not put the point in there. So this is technically the error that they give you. And then this tells you the error in the volume. So final answer is like 32/100 pi in either direction. So that one just kind of has a process. Take the derivative with respect to the radius in this case. And this is the error in the radius. This is the error in the volume. So they give us the radius is correct within this much. So this is the error in the radius. And they're asking us for the error of the volume. And you just plug in what they give you. Next one. If the local linear approximation of f of x equals 3 sine x plus e to the 3x power at x equals 2, it's fun to read math, right? If the local linear approximation of f of x is used to find the approximation for 1.9, f of 1.9, so that's the one like we did 2 examples ago, then what is the percent error of this approximation? Okay, so let's do that whole process again. They're telling us local linear approximation at x equals 2 is used to find the approximation here. So this is like that example where I drew the tangent line and I said that this is x equals 2 right here. At x equals 1.9, it's super close. Same kind of idea. So let's find these examples or these answers. F of 2 using this function, derivative of 2 using that function. So f of 2, we plug in a 2. We're going to need a calculator for this one. It's a nasty one. The derivative when x equals 2, so 3 cosine x, and then we're going to have e to the 3x times 3, and then plug in that 2. Use your calculator for that too. So this is icky, but we're plugging it in now. So now this is f of 2 right here. This is the derivative when x equals 2, and then the x coordinate is 2. So I just plugged it into the point slope equation right there. And then remember, we're using this tangent line to approximate this point on the f of x graph. So let me solve for y. I just distributed there, and then I'm going to add that 406 number and get my y equals equation. This is the equation for the tangent line. Plug in the 1.9, and that gives me the point of f of x approximately at 1.9. Okay, so we have the approximate value of f of 1.9. That's not what the question is asking. They're asking what the percent of error is. So how close are we? If this is the approximate value of this point, what's the percent of error? How close are we? So what you need to do is remember that percent of error, it's the difference between the estimate and the actual value divided by the actual. The difference, oh my goodness, there we go, over the actual. So we have to figure out what the actual is and subtract it from the estimate, that's the numerator, and then divide it by the actual amount. So we need the actual value of f of 1.9. And we were given f of x up here, so we can find that. Okay, f of 1.9, plug in, use a calculator. This is the actual value of f of x at 1.9. So the percent of error is the difference between the estimate and the actual divided by the actual. So you take the 285 number, take it away from the actual value of 301, and then divide it by the actual value of 301. So it's approximately 5.45% off. And it doesn't matter if it's negative or positive, it's an absolute value here. We don't know what direction it is. We don't quite know if the graph is concave up or concave down at that point. We don't know if the tangent line lies above or lies below, because concavity determines where the tangent line falls. So if the tangent line is above, then our estimate is larger, and this would be a larger number. If the tangent line is below, then our estimate is smaller.